Pleasant good morning to one and all present here. I welcome you all to the eighth session of the workshop series of CIT Quantum Hackathon 2022. I hope all of you enjoy and learn something new daily through our sessions. I take privilege in welcoming Mr. Prajjwal, software development engineer with Amazon. Sir has completed his Bachelor's of Engineering in CS and MSc in Economics at BITS Pilani, Hyderabad. He became a cricket advocate in 2021. He has been actively participating and contributing for Qiskit and quantum computing since 2020. Sir is now mentoring many various IBM hackathons and courses and workshops like this. Thanks for taking your time to share your knowledge with us, sir. We are very eager in hearing about the quantum teleportation.
Thanks for that introduction, Dharani.
Yes, sir.
It's a little weird hearing myself being referred to as sir when I just graduated from college in the last month itself.
Yeah.
So yeah, I'll just share my screen and let's get started. Okay. So quantum teleportation is today's session, and it is. Yeah, I understand that you all have had a session on quantum entanglement just this morning earlier. So we will. So this is a topic that is slightly dependent on that, but it's entanglement and teleportation are simple enough to understand. So you need not worry if you missed morning session also. So, just I'll just set some expectations. What this session is not about is teleporting yourself from place to place, because if that was possible, then I would probably be giving this lecture in person rather than online. So, so let's just have a quick recap of quantum entanglement. Can anyone tell me whether this state is entangled or not? You can send your message in the chat or feel free to unmute yourself. Is this quantum state entangled or not? Okay. So this is not an entangled state because it can be separated out as a factor. It can be separated out into two individual qubit states, which is against the definition of uh, two qubits being entangled. So this is not an entangled quantum state. What about this one? You might have come across this a few times already in your previous sessions. Yeah, so this is entangled because it has no common factors which you can separate out. You can't write it as a tensor product of two different single qubit states. And what about this one? Okay, this is also entangled. So yeah, that's right. Seems like you have a pretty good grip on entanglement. Now for some theory questions. Is quantum entanglement possible with one qubit? Okay. Quantum entanglement is not possible with a single qubit because entanglement is a phenomenon that in which two qubits interact with each other and influence each other to take certain states after one is measured or there are two or more qubits which influence each other. So that's right. And so do entangled qubits need to be near each other to influence one another? That's right. They don't need to be near each other. Uh, and the distance between two entangled particles doesn't matter. Uh, when you measure one, the state of the other immediately, instantaneously changes to whatever it is correlated to change to. Uh, so yeah, distance is not a factor. Now, can someone give me a 3-qubit entangled state? Take a minute to answer. So 3 qubits entangled with each other. You can type your answer in the chat. Okay. Uh, so I am putting my answer into the chat. So 000 plus 111 with the appropriate normalization. This is a 3-qubit maximally entangled state. So yeah, just like the common Bell state, 00 plus 11, you can have. So this is a direct derivation. You can. This is a direct 3-qubit entangled quantum state similar to that one. So yeah. Uh, and in this, you can see if one of the qubits is measured to be 0, then the remaining two also become 0. They will definitely be measured as 0. And if any of them are measured as 1, then the remaining two will also be measured as 1. Hence, they are entangled. So, moving on, you answered most of the questions correctly. So still, you still remember enough quantum entanglement to continue. Just a warning. So what you're going to learn about and see, it's not all science fiction. It has been practically performed by experts and professionals in extremely controlled environments. But performing them at home is not possible yet. But we'll come back to this practically performing these experiments. It was recently in the news, so we'll come back to that at the end. So here are Alice and Bob. I believe you're good friends with them now from your previous sessions. If not, you're just getting started in quantum computing, and you'll find them in a lot of places. So Alice and Bob have want to perform quantum teleportation. So they each have a qubit in the state 0. So 0A signifies Alice's qubit, 0B signifies Bob's qubit. And in order to perform quantum teleportation, they first need their qubits to be entangled. So because uh, for teleportation to happen, the entanglement is the channel through which the teleportation is going to happen. So Alice will have another qubit which she wants to teleport, the state of which she wants to teleport to Bob. And since these two qubits are entangled, we will see in the coming slides that since they're entangled, Alice can do a few things on her side so that the state that she wants to send becomes the state of Bob's qubit, and Bob can use that qubit as he pleases. So this particular state is a normal Bell state, and how to construct it is simple, like having a Hadamard gate and then a CX gate from one qubit to the other. This gives you an entangled state between both the qubits, and we have to write it together because as I said, we can't separate out entangled state into single qubits. So uh, now that they have entangled their qubits, uh, I, it doesn't matter what is the distance between them. So let's just say that Alice goes to space, and where she takes her qubit along with her. But still remember that they are still entangled. This is the state of their qubit, of their qubits. So if Alice measures 0 and 1 qubit, then Bob's qubit, if he measures, will also be 0. And if Alice measures a 1, then Bob's qubit will be a 1. Right now, nobody is measuring anything. Just keep in mind that this is the current state of the qubit, even though Alice has gone to space. So, keeping this state in mind, now Bob is on Earth and Alice is in space. And suppose now Alice has a third qubit, uh, which which has this particular state alpha 0 plus beta 1. And this should become the state of Bob's qubit at the end of our teleportation experiment. So, what Alice will do is that she will make this particular state or this particular qubit interact with her entangled qubit, so that all three of them become part of like all this three qubit system becomes even more like interactive with each other, or there are dependencies established these three between the three qubits. So uh, what so these are the two operations that Alice will perform, and we will look in the next few slides how these two operations change the state, and ultimately how that helps Bob to get this particular state psi on on the ground while Alice is still in space. So our goal ultimately is to have Bob's qubit have this alpha and beta coefficients along with uh, his 0 and 1 state. Any questions so far? Any questions so far? You can unmute or you can type your questions in the uh, chat. So initially, Bob and Alice had a 0, 0 qubit. They entangled it using the Bell circuit with one Hadamard and one CX. And then Alice has taken her qubit. Uh, she hasn't observed it yet. She hasn't measured it yet. So it's still entangled with Bob's qubit. And she is in space and she wants to teleport a new qubit state using her qubit to Bob's qubit. This is the summary so far. So, yeah, I'm assuming no questions so far. So let's just look at what this other CX and this other H Hadamard gate due to the quantum state. So if we write the quantum state of the entire three qubit system, so this particular quantum state is this is the state psi which Alice wants to send, and this is the state of the remaining two qubits which Alice and Bob have. So if we rewrite this tensor product, then we will have four terms in the state with appropriate normalization factor. I think I missed that. There is a root 2 that is supposed to be here. So if we just open the brackets or perform the tensor product, we can rewrite the state as 0, 0, 0 with alpha, 0, 1, 1 with alpha. So this is a normal, like you're just multiplying each term with each term. So this particular state is currently the state of the 3-qubit system before applying the additional CX and Hadamard gates. If we apply the CX gate between the first two qubits alone, so 0, 0 will not have any impact due to the CX gate, because for CX to work, the control qubit needs to be 1. So nothing will change in this first term. Nothing will change in the second term as well, because this also the first qubit is 0. But in the bottom two, the states with beta as their coefficient, since the first qubit is 1, the second qubit will and the X gate will be applied to the second qubit because it is a CX gate controlled on 1. And similarly, for this term also, this will become 1, 0A, 1B. So, is everyone following? Would you like me to repeat? Do you have any questions? You can also write if it's fine and I can proceed. Okay. So far we have opened the brackets and we have applied the CX gate. So you can see this second term, this third term, beta 1 0 A 0 B became 1 1 A 0 B. And this last term, beta 1 1 A 1 B became 1 0 A 1 B because of the CX. And the normalization factor is present. So yeah, these are the changes. So this is the current state, the state which we ended with in the previous slide. And now we apply a Hadamard gate on the first qubit. So on if we apply Hadamard on the first qubit alone, can someone tell me how many states we will end up with on the RHS if we apply Hadamard only on the first qubit, the leftmost qubit in each term? Currently we have 4 terms. How many will how many terms will our resulting state have after applying the Hadamard? You can take a guess by thinking of a normal 0 state, and if we apply a Hadamard, the number of states become 2 times. So here also, since we are applying Hadamard on the leftmost qubit of each of these terms, so each of these terms will split into 2, one with 0 and one with 0 and one with 1, with appropriate signs, and we will have a total of eight states, the 8 possible states in the superposition. So this is so for each of these 4 terms, these are the 4 outcomes of applying the Hadamard. So as you can see, in the first state 0 0 0, when we applied Hadamard on the leftmost qubit, it became 0 0 0 and 1 0 0. Likewise, for the second state, leftmost qubit was 0, so we have a 0 and 1 as the leftmost qubit in its RHS side, and the remaining 2 qubits are the same. And if you remember, Hadamard applied on a 1 state uh, gives us 0 minus 1 with appropriate normalization. So here all the coefficients which are present with beta and I have a 1 like in the result of the Hadamard, they're all negative. So 0 1 0 1A 0B minus 1 1A 0B, and for the fourth state also. And you should notice that since we applied another Hadamard, that factor of 1 by root 2 is multiplied by the existing one, and total, since we have eight, so in total, the normalization factor for this is 2 at the bottom. So you might be wondering, there are 8 states. Why is the factor only 2? Because if we square 2, we get only 4, and we can have only 4. We should have only 4 states if they're all equiprobable. But keep in mind that these states by themselves also have some coefficients alpha and beta, which are normalized in themselves. So this additional by 2 is for apart from after alpha and beta, what is the remaining normalization. So yeah. So now what we need to do is, there is a pattern which, like on this slide, it might not be apparent. So we will rearrange these terms in a pattern in which, if you see, like we can use measurement and entanglement, so that Bob is able to get the alpha and beta on his qubit, which is teleported from Alice's qubit. So, so if I hope you remember, Alice has 2 qubits in space with her, which are the first 2 qubits of every term. So 0A is the qubit she originally started with, and the one without a subscript is part of the information qubit which she wants to teleport to Bob. It's part of the psi alpha 0 plus beta 1 term which we started with. So now we will rearrange the uh, terms of the last state which we saw. So if you notice, since Alice has the first 2 qubits, we will try to rearrange with respect to those first 2 qubits. Uh, so if we take in these two terms, you can see 0, 0, A, 0, 0, A is common. So uh, what would that, if we take that common, what would that term become? Like that term alone, like those two terms, if we rearrange them and we write them like as a factor in a factorized form, can someone tell me what it might become? You can take a guess. We are taking the first 2 qubits common, and we want to write, we'll write the third qubit in a bracket like as a sum. Maybe if you see the first one, it might become apparent what I was expecting. But so we can rearrange the term, these two terms, and we can rewrite them in this form. Does anyone have any questions about this? Yes, no? Okay. So, so the 2 qubits Alice has are 0 and 0A, and the third qubit can be rewritten. So here we're not performing any operations, we are just rearranging the terms of the expression, which, like, this is just for our convenience, just to make the point which I'm trying to make. If we rearrange them like this, the next, so we take 0, 1 common next, and we have alpha 1 and beta 0. Similarly, 1, 0, we have alpha 0 minus beta 1. And finally, the last 2 terms. So we have taken all the 8 terms, we have rearranged them like this. So now can somebody tell me what happens if Alice measures these 2 qubits, the first 2 qubits she has? So in one of your previous sessions, you might have learned that there are Like if you measure superposition collapses, right? So here we have a superposition of 8 states. What happens if Alice measures the first 2 qubits, or the only 2 qubits she has? If she measures both of them, what will the resulting state of Bob's qubit be? So think about that. Meanwhile, I'll just tell you. So in this particular arrangement, you can see that 00A is associated with alpha 0B and beta 1B, right? So this is what entanglement is. If like this particular, if the first 2 qubits turn out to be 00, then Bob's qubit takes this state, becomes this state, because if these two are 0 and 0, if Alice's qubits are 0 and 0, then Bob's qubit can only take this particular form. So likewise with all the other possible measurements that Alice can make, there are some associated states that Bob's qubit will definitely take if uh, if Alice's 2 qubits are measured in that particular, like in their preceding common factor states of Alice's qubits. So if Alice can measure, so there are 4 possibilities that Alice can measure, or Alice can get when she performs the measurement on her 2 qubits. So she can either get 00, or she can get 01, or she can get 10, or 11. So if she gets 00, then the qubits on her side have collapsed, and measurement has destroyed the entanglement also. But the information has been preserved in the form of alpha and beta, associated with 0 and 1. But that is only the case for 00. If she measures 01, then you can see that 1 and 0 are not associated with alpha and beta as they are supposed to be. They are associated with the opposite thing. I hope everyone is following. Are there any questions about this or what I explained so far about the association between Alice's qubits, and the resulting state which Bob's qubit will have?
Sir, one question.
Yes.
Measurement we are doing one after the other, right? Assume that I don't know if practically you can measure. If you measure all the Alice and Bob's qubits simultaneously at the same time, is it
Mhm.
what will be the result?
So if all 3 qubits are measured, then all the information will be lost. So again, if we measure all 3 qubits, then any of the 8 possible states in 3 qubits can be measured, and alpha and beta will be lost because the entire superposition will collapse as all 3 qubits have been measured.
Okay. If only two qubits are there, many times we hear like measuring one will affect another one actually. If you
Yes.
measure only two qubits simultaneously, that time also, I mean, this equilibrium will be lost, right? I mean, whatever
So,
the
yeah, so right now, if you see, there are 8 states uh,
correct,
in the entire term. So if we measure 2 qubits, that means like we are removing 4 states.
correct,
Sorry, not 4 states. We are dividing the states by 2. So 2 possibilities get cancelled out with each qubit we measure. So or half the possibilities go if we measure 2 qubits. So if we measure the first one to be 0, then the second one, the qubit with subscript A, it can still be 0 or 1. But since we measured the first qubit as 0, it cannot take any of the bottom 2 states, right?
correct.
So the
Right.
bottom 2 states have been lost. So they are collapsed. because we measured the first qubit as 0. Likewise, if we would have measured the first qubit state as 1, then the uh, top two parts of the or the top two terms out of these four would have been lost.
Okay. Thank you.
So if we measure, if Alice measures the second qubit, which she has also, which is the second qubit in 000110 or 11. So if she gets, so in the remaining, if she measured the first state as 0 and the second state as 0 again, then the remaining third qubit, which is unmeasured, can only have this alpha 0b plus beta 1b,
Okay.
right?
Yeah. Yeah.
Yeah. And if Alice measures 0, 1, then Bob's qubit becomes alpha 1b plus beta 0b.
Okay.
I hope it's clear to the rest of the people as well.
Yeah. Another question, sir, like this
Yes.
teleportation, right? Here, the only information will be transported, right? I mean, not the actual, I mean, matter, I mean, whatever the
Yeah.
molecule or something.
Right.
Yeah. In reality, what is the medium of communication actually to visualize it, right? Is it kind of RF medium or is it kind of waves?
So entanglement, like it, and the effect of entanglement is not like medium related, right? If you have the state change happens simultaneously. So we are transferring the state of one qubit to state of another qubit, which is the same thing. We're transferring the information contained in one qubit to another qubit placed far away, and that is possible since we are breaking, like since they are entangled first of all, and since we are measuring, we are breaking the superposition, or we are collapsing two qubits so that the third qubit can get that particular state. So there is no medium as such for entanglement. It just happens instantaneously. So a common example for entanglement which is given is if you randomly put two gloves, like one left hand glove, one right hand glove, without seeing which you are putting in which box. Close the box, take them a lot, like very far apart. If one person opens the box and finds a left hand glove, like before opening the box, both the boxes can have uh, either of the gloves. We don't know.
Correct.
But like if one box is open, then immediately it is determined. We don't need to open the box also. Like if we have a left hand glove in one box, then instantaneously we can say that the other glove has manifested or it has collapsed to become the right hand glove.
Got it.
Yeah.
Sir,
So
so isn't it all about the wave-like behavior? So this initiation, its initiation is from quantum mechanics, and where we study about the wave function and all.
So wave functions are also, correct me if I'm wrong, wave functions are also like probability distribution sort of thing, right? For a particular uh, qubit. So once we measure, the wave function also collapses. So for we are transferring the wave function, but like through entanglement, the wave function which was there present in the qubit which Alice wants to send. Now that has become the property the of Bob's qubit because Alice has collapsed the wave function for 0 and 1. Sorry, for her two qubits.
Okay, sir.
Yeah. So, uh, yeah. So the state which Alice's first qubit had, since she has measured, that state is lost, but that state has been transferred to Bob's qubit because And so that is like part of what I find beautiful about quantum teleportation. Like it's just like you rearrange the math and you get these four possibilities which are entangled with like each of these measurement outcomes. You have one particular state of Bob's qubit, which uh, yeah, which you can from which we can derive what Alice's original qubit which you wanted to send was. So there is also a bottleneck in this teleportation equation. So yeah. So now I'll talk about the bottleneck in a few minutes. So if you notice in these states, if Alice measures 0 0, then just if you think of this remaining third qubit state without the subscripts of B, then we have the same psi that we originally wanted to teleport. In this second case, we have, as I said earlier, alpha and beta are associated with 0 and 1. Like they're associated with the opposite states than what they're supposed to be. Like Alice wanted to send alpha 0 and beta 1, but instead, if she measures 0 1, then Alice knows that Bob's qubit would have become 1 0, like with the coefficients attached strongly. So, can someone tell me? I think you've had a session on gates as well, right? Can someone tell me which gate Bob can use to convert this alpha 1 B plus beta 0 B to the required state which Alice originally wanted to transfer? Just look at the second term, the part in brackets. Which gate can Bob use to apply to this alpha 1 plus beta 0 to get alpha 0 plus beta 1?
Bit flip, sir.
Yes, bit flip or the X gate or the NOT gate as it is called. So, and similarly, then I'll ask for the third term, what would be the change required? In the third term, to convert from alpha 0b minus beta 1b, which gate can be applied to change the minus to plus basically. Yeah, so that's right, Mohammed. We can apply the Z gate or the phase flip gate, which acts on 1 and converts and flips the sign to from minus to plus. And so the last one, does anybody want to take a guess or should I reveal? In the last one, we want to perform both of them. So in both the states 0 and 1 are uh, 0 and 1 are attached to opposite coefficients, and there is a minus instead of a plus. So for the last one, we can first apply the X gate so that 0 and 1 are associated with the right coefficients, and then perform the phase flip, which will convert the minus to plus, and the plus will be, of course, associated with beta. So this is the summary table of what Alice measures, then the resulting state of Bob's qubit. I have removed the subscript so that it is clearer, the subscripts don't matter. So just for this general table, if Alice measures 0 1 0 0 in the first two qubits, then Bob's qubit is what we want. So Bob doesn't have to do anything, or he can just apply the identity gate, and his final state will be psi. Keep in mind, this is like a lot of people get confused that the final, like Bob is not doing any measurements. Bob just knows that Alice will perform the measurements, and like he once she performs the measurement, he will have to apply one of these gates, which don't measure the qubit. They're just normal quantum gates, which just convert the state from one to another, and he will have the final state. So first case, he doesn't have to do anything. Second case, as you said, uh, bit flip or X gate is sufficient, and the final state will be the psi that we wanted. Third case Z, and the last case, first we apply X. So we go from right to left. So first we apply X and then we apply Z. And in all the cases, Bob has the final state, which uh, Alice had initially, which she wanted to teleport. Now, there is one missing piece which I haven't told you about so far. Can anybody guess what that is? So Alice measures, and Bob has to apply some gates associated with those measurements. But there is something in between that has to happen, which is also the bottleneck of this quantum teleportation algorithm.
Sir, how would Bob knows what gate to be applied even if Alice doesn't conveys the what state she had measured like that?
Correct. So that is why Alice will have to use classical means to convey what state she measured, and based on that, uh, like Bob can be ready with conditional operations on his circuit, uh, and like based on what Alice sends through. So once Alice has measured, then her qubits are no longer in quantum states. They are similar to classical states. So Alice will have to send that classical information through classical channels to convey to Bob that this is what I measured, and you can apply the appropriate operations to get the state that you want. So this is the overall quantum circuit, which which we are which we have seen in this entire lecture. So initially, the two qubits, Alice's first qubit, and so Alice's qubit, which she started out with, and Bob's qubit are entangled using the normal Bell circuit. Then once Alice has the third qubit which she wants to send, like it can be initialized in any alpha beta, like with any alpha beta in any state. Once she has that, she can make it interact with her part of the entangled pair of qubits through these two operations. And with this, we get the state associated with the probabilities, like, state associated with each of Alice's possible measurements. So Alice then measures her two qubits, and based on those two measurements, uh, Bob applies the X and Z gate. So this gate, if yeah, I'm not sure if you have seen before, so these are conditional operations. So conditional on the classical register's values. So if this CRX classical register has a value of 1, then X will be applied. If Z has to be applied, or if the CRZ classical register or bit is 1, then Z will also be applied. If they are 0, then the respective measurements are not applied. So yeah. Uh, so this happens on Bob's end, and this particular measurement is happening on Alice's end. Mm, so yeah, this again just going through the states. Initially 0 0, then entangled. Then at after these two operations, we have this associated pairs of Alice measurement and Bob's resulting qubit. And at the end, in any case, Bob has the state that Alice originally wanted to send. So the state of the qubit can be considered as teleported as soon as Alice performed the measurements. Yeah. So so this we can have a Q&A, but before Q&A, like recently, if you saw the news, teleportation is not this like for information transfer. Quantum teleportation has been performed in like labs and on large scale as well across many kilometers. Currently, the record for quantum teleportation is like over, I think, 1400 kilometers apart. Qubits have influenced each other, and the state of one qubit has been transferred to another qubit. And this was performed via like one entangled qubit or a few entangled qubits remaining on Earth, while another qubit was taken to space, and like teleportation protocol was performed between those two. So that is the current record. And like the teleportation algorithm was first experimentally shown in 1997 by Anton Zeilinger. I think the name is Zeilinger. He's one of the recipients of the Nobel Peace Prize because of his efforts with, sorry, Nobel Physics Prize this year. Like it was announced a few days back. So, among the three recipients of the Nobel Prize, Zeilinger is one of them for his work on quantum entanglement and quantum teleportation, which today is contributing to advancement of quantum communications and quantum internet. And Zeilinger was also a part of this experiment, like performing it across, like with the satellite and on Earth. Uh, this record, which is currently set. Yeah. So that is about them. So to run this on Qiskit, one second. I will just stop sharing and share a different window. Uh, so any questions right now?
Sir,
Yes.
sir, you told about the bottleneck that is happening in entanglement, sir. So, what are all the current active researches going on that to reduce this, or if it is the condition, the entanglement property it is not useful, right, sir? Because we have to transmit our data classically, so it won't be at that speed and it won't be that effective, right, sir? So what are all they doing, and is it possible to reduce this bottleneck, sir?
Yeah, so in the notebook which we have, and I think on Qiskit as well, on the Qiskit textbook as well, uh, they have mentioned that like all the measurements can ideally be moved to the end of the equation. So end of the circuit, sorry. So Alice doesn't have to perform the measurements. We can just apply conditional, we can apply quantum gates instead of conditional if gates to like we can keep the state quantum itself. We don't need to measure and then convey. So I'll just share that notebook. Maybe at the end of that, we will be able, you will get an answer to your questions and you can explore further. But okay, let's share an entire screen. I hope we have enough time. Okay. Yeah. So this notebook is the same one which is like on the teleportation, which on the Qiskit textbook, whatever the content is there, this is the same notebook. So we have this like the setting up of the teleportation scenario. So, so Alice and Bob are given their entangled qubits. Qubit state. Uh, when Alice sends her classical bits, the entangled state that she wants to send to Bob, uh, when she measures, the entangled state is sent, and Bob receives that based on whatever operations he has to apply. So in creating the notebook basically has one function for creating the bell pair, creating quantum registers, 3 qubits and 2 classical bits as we saw. So if we'll run this qubit, we'll run this notebook also. Hopefully, this. Okay, 1 second. Skip. So, definition of this, then teleportation circuit. Initially, we have this bell circuit. Then Alice applies a C naught. So Alice's gates are Cx and H applied one after the other on the qubit which she has, which is denoted by A, and the psi which she wants to send, and this QC is the circuit on which she wants to apply. So that is passed as arguments. So step 1 was creating the bell pair. Step 2, Alice's gates are performed. This is the circuit diagram. Then we have the measure and send parts. And with step 3, this is what it looks like, the circuit. And then Bob has to apply his gates, which are dependent on the values in the classical registers. So this is the diagram we saw in the PPT. Now, on a quantum computer, if we take ideal state, so suppose this is the psi that we want to send, which we want to teleport. So this is alpha, this first term, and this part is beta. So you would have learned in previous sessions that alpha and beta can be complex numbers. So this is a single qubit state of alpha and beta. This way, I'll just this is better in light. Okay. So alpha and beta are these two complex numbers, and this is the representation on the block sphere. So this is a. So have you had a session describing block sphere?
Yes, sir.
Yeah. Okay. So you recognize this. So this is where the state. This is the position of the state vector in the block sphere for this particular size state which we want to send. In order to verify, so we are visualizing this now, and after teleporting, when we visualize the state of the third qubit, we will verify that this state and the third qubit at the end of teleportation is the same. So this is okay, the state and the cell again. So this is the new state which we want to teleport, and we initialize the qubit which we want to send in that state. So ultimately, this is the initialization of the creation of the third information qubit. And if we use this simulator and we save the state vector, then we have, so you can see qubit 1 is in one state, which qubit 0 is in one state, which is Alice's first qubit, which was initially qubit 0 was this state. Now it is in one state because Alice has measured, so it has collapsed, and it has collapsed into one state. So we have 1 and 0. Alice got 1 and 0 in her measurements, and after, since the circuit already contains the gates to be applied, after those respective x and z as required are applied, this is the final state of Bob's qubit. So comparing this to this particular thing, you can see that they are the same states. So now to verify that on a proper quantum computer, we can't have like we can't measure a state vector in we can't get a state vector out of a quantum computer. That is just a property of simulators. So what we can do additionally is the state that is received by Bob, we can run the inverse initialization gates that we ran, and ideally, if Bob has actually received the required state, then applying those inverse initialization gates should take psi from psi to 0, because initially when we initialize that state, it was taken from 0 to psi. If we apply the inverse gates, then we should be able to measure 0. So, so this additional operation we're doing is just for verification purpose and to get the information out of the quantum computer on which we, or on the quantum processor that we run run the circuit. So this will act as a verification for our teleportation protocol, whether it's happening as expected or not. So again, we have all these steps, and additionally, I forgot to initialize. One second. Additionally, we will have the inverse disentangler state, or they're just calling it disentangler. This is the inverse of this particular initial operation that was performed. So if Q2 really has psi, then this disentangler should leave the final state at 0. Does anyone have any questions about what the disentangler is doing? No?
Sir, I couldn't get it, sir.
Okay. So initially we use some gates to initialize the random quantum state, right? We want to make psi over here, right?
Yes,
You
sir.
got
Yes,
it?
sir.
Yeah. So some gates are applied there. And finally, we are expecting, like before this disentangler, this Q2 also has the same state, which was initially present on Q0,
Okay,
right?
sir. Okay, sir. Okay, sir.
So now if we apply the reverse gates of what we did here, then we should get 0 at the end, right? So Q0 was initially in 0. We use these gates to make it psi. We have psi here. We want to make it 0. So we will use the reverse gates over here. We want to make it 0 just if it is if the state is not 0 at the end of the disentangler, that means before the disentangler we didn't get the same state that we wanted earlier. So that is the verification we are performing.
Okay, sir.
Okay, cool then. So if we add registers to measure, now we want the verification step, we take another classical bit and we measure, and we expect it to come to 0. So if we run our experiment on the ideal case, you see this is the third qubits measurement. These two are these two are basically the other two qubits which are there, but other two qubits and what they were measured as and how often. So we don't need to look at these things because they will have come out in all sorts of all possible Alice's measurements like 0, 0, 0, 1, 1, 0 and 1, 1. But what we are interested in is only this particular thing. So this graph is basically showing, one second. This graph is basically showing that the third qubit was always measured to be in 0. Okay, so that means our teleportation is working properly. But this is the ideal case. This is a simulator case. That is why we are getting a perfect 0 every time. So this 100% chance of measuring is due to the ideal simulator. This is again some of the math which we did earlier. These are the associations. The gates that Bob applies. And now there is a concept of deferred measurement, which you were asking earlier. So what we do is, instead of this whole operation where Alice measures, then sends the qubit to Bob, and then Bob applies based on that. Bob applies this thing. Alice can directly apply a controlled Z gate on the third qubit. So this Z gate will be applied on based on, like, okay, so we have a Z gate if the first qubit is measured as 1. So in 1 0 case. So if Alice's first qubit is 1, then we should perform the Z operation, right? That is what we are doing over here also. Is this clear?
Yes, sir. Yes, sir.
Cool. So similarly, Alice can do a CX, additional CX also, to avoid the measurement routine for the other qubit also. So now new Bob's gates, or Bob can also apply them. Alice doesn't have to, but like, okay, so they will have to come back together for this to happen, or maybe in the future we'll have some other means. But yeah, so new gates which Bob will apply instead of this conditional on classical measurement, classical instead of the conditional operation conditional Z that they are applying based on the classical register value, Bob is directly applying the quantum CX gate and the quantum CZ gate. And based on that, our initial our circuit changes to this. So instead of the measurement operations, we have CX and CZ. And then we again verify with the disentangler that the final thing is 0. Now, if we execute on a real device, I ran a job yesterday night because uh, there is a queue that we will have to be part of if we run it now. So, uh, I ran one experiment last night on real quantum hardware, and you can see the measurement outcome of this particular measurement. This is the only measurement which is now present in the entire circuit. So the measurement outcome of this was 0, the percentage. So out of 4,000 shots, 3,754 were zeros, and this was 1. These many were 1. So if there is a percentage somewhere. So okay, fine. You can see that maybe 90 greater than 90%, almost 93% uh, of the measurement outcomes were the desired 0 outcome, and this particular one, the few ones that we received are because of you should know this by now. Why would we have gotten the ones? Mm, we're trying to verify that we get everything 0, but this is real quantum hardware, so we have a few ones because of the noise which is present either in the qubits which are created in the gates that were applied, or during measurement also there can be a few uh, like there can be readout errors or measurement errors. So those we can attribute the few ones that we got to that uh, to those errors. So this is performed on real hardware, but it is on a single chip. So again, the distance advantage is not clearly visible, but you are all free to go to check out the press release from Nobel or the news around the Nobel Prize this time to see like what experiments are being performed with quantum entanglement, how we're bringing to reality like quantum communications, quantum internet, and all those are great research areas that are currently actively like being done by companies, research institutes. So yeah, maybe some of you will also be part of the revolutions, hopefully. Yeah. So I will stop my screen share, and I hope this was useful.
Yes, sir, it was completely
Are
useful.
there any more questions regarding teleportation or quantum computing or Qiskit advocate? How you can contribute, how you can get in? Maybe one of you will be lecturing at another event next year.
Sir, my question is very generic actually.
Yes.
Is there any, because many times when you start quantum, right, I'll be ending up physics side, chemistry side actually.
Mm-hmm.
My profession mainly into the product manager. I have the experience around 16 to 18 experience into networking, mainly into wireless area.
Mm-hmm.
I want to know something where on the project manager, any kind of course where project management or product management kind of with respect to the quantum, right? Just I want to shape my career from the product into a wireless into area into the, I mean, quantum area. I don't know where I have to focus thing because when I start, no, I'm getting blockage on the chemistry side, physics side, or like when I go to the gate side, right? I don't know how I have to shape my career mainly into the quantum, carrying my existing experience.
Okay. So like there have been like there are people who would be working in quantum computing companies as product managers and all.
Correct.
So yeah. So I don't have an answer on the top of my head, but there are a few references like in past events, in usually like global events that IBM conducts, there is a panel discussion towards the end, or sometimes there is just a normal talk which is uploaded on the Qiskit channel where you can find similar questions. Like, there are non-tech jobs in quantum as well, and not just IBM Quantum. There are others also, other podcasts which might
Okay.
like discuss this topic. The non-tech jobs, not everything requires like knowledge of physics and chemistry.
True.
So yeah, I can only suggest you try to look at those.
Sure. Thank you, sir.
Yeah, and you can also like okay, yours was a career-related question, but in order to you can also post your question on Qiskit Slack where like people are always ready to help somebody who has more knowledge about this, maybe somebody also who is working within IBM in a similar role can help you out. So feel free to post on the relevant channel on Qiskit Slack, maybe on
Okay.
general or yeah.
Sure, sir. Thank you.
Sir, can you please share your email ID for future reference for contacting you about this type of?
Yeah, sure. You can. I'm already available on Discord. Maybe I'll share it there. I'll share it with you. Just send me a message on Discord or Slack. I'll share my email ID there.
Sure, sir.
Yeah, or maybe in the hackathon Discord server. Yeah. Any other questions? Yeah. So the Qiskit Slack link is shared by Dharani on the chat. You can join there.
Thank you.
Okay.
So I guess we have arrived at the end of our session now. If any participants have any doubt, you can clarify it now.
Yeah, and as Manjula ma'am suggested in the start, I'll start being more active on the Discord server, and maybe you can ask some follow-up questions. Maybe when you revisit the topic, you might have some doubts. So I'll try to answer over there as well. Yeah.
Sure. It was an interesting session, sir. And I once again extend my gratitude for you joining hands with us. And also, I would like to thank Dr. Manjula Gandhi for constantly leading and supporting us. And once again, thank all the participants for joining this session and making it wonderful. We are always available on Discord. You can ping us there if you have any doubt.
Yeah. Thank you
Thank,
again. Thank you for the Biscuit Fall Fest, and thanks for inviting me.
Yes, sir, it is our
thank
pleasure.
you, sir.
Yeah.